The broadcast is now starting. All attendees are in listen-only mode.
Okay, good morning, good afternoon, good evening, wherever you are in the world. This is Krishna Vedula from UMass Lowell, Boston area. Just welcoming you all to one more of our very distinguished and exciting presentations on behalf of the IFES Global Webinar Series. And we have with us Dr. Professor James Trevelyan from the University of Australia, and he will be talking to us about engineering and the UN Sustainable Development Goals. And he told me not to read his extensive abstract, so I'm just going to put it up there. I'm assuming that you have had a chance to to browse through it. So without much ado, I'm going to make him the presenter. And we'll be off to the races here. Just give me a second. And just to remind you, while he's getting set up, that please text any questions that you have on the text feature on the right-hand side. And look at that beautiful scenery there from Australia. Okay, James, you're on.
Thank you very much, Krishna, and it's a great privilege and honor to be talking to you all today, wherever you are around the world. And this indeed is a picture from Central Australia. We have beautiful night skies, and that's just like the tourist advertisement. Please come and visit us one day. Although today I'm speaking to you from grey and cloudy England. So this talk is all about my ideas about engineering that have emerged from 20 years or so of research on engineering practice and many experiences in India and Pakistan. I spend about 1 or 2 months a year in South Asia. So I want to address this talk particularly to all of you listening from India, Pakistan, Bangladesh, Sri Lanka, Maldives, and the South Asian part of the world, although it has relevance for many other developing countries and in fact developed countries. So I want to just start off with this idea for you. I suggest that the great innovations of this century will come from an understanding of people and technology.
James, can you close that screen on the right? I think click on the red arrow. It'll hide. It'll become hidden. On the red arrow. There you go. Yeah. Yeah. You're fine now. You're fine.
Okay. Yes. Thank you. Sorry about that, Krishna. The engineering education research community is best to solve these, is best to come up with these innovations because this community brings an understanding of human behavior into engineering faculties, perhaps more than any other, and in a different way to what we've seen before. I also want to talk to you as the director of this company, Close Comfort, and I'm going to bring this more into the talk later. It's important that you understand that I'm not a normal engineering academic. I spent 40 years teaching and researching engineering at the University of Western Australia. And now, the last 3 years, I've been learning to be an entrepreneur. So I introduced myself as a young and inexperienced entrepreneur. I also, of course, continued my research on engineering practice, and some publications are still coming out. So this is an outline of the talk. I want to start with ideas on engineering and productivity. Here is some data from McKinsey produced 3 years ago, which shows the level of developed world productivity. And what we see is highlighted is Australia, which increased from a measure of $45,000 purchasing power parity per person in 1964 to $95,000 per person in 2012. And what we see is on the right-hand side is the change relative to the US. So Australia has slightly improved relative to the US, but pretty much we've kept pace. More importantly, let's have a look at the next picture. This is the emerging world productivity, and I've highlighted the values for India. It's really interesting to see that India and China are not so far apart from each other. And what we see in the world is a large group of countries which have around about 5 times less productivity than the advanced industrialized countries. Now, interestingly, that ratio, 5 to 1, has not shifted in decades. And only 2 or 3 countries have managed the transition from being an emerging, developing economy to an advanced industrialized or post-industrialized economy. Singapore and South Korea would be 2 notable examples, and both have existential reasons for that transformation. So what we're seeing here is an extremely stable pattern in economic development around the world. But just because it seems stable doesn't mean to say that it can't be changed. What I'm going to argue in this talk is that engineering is a factor that has been overlooked in discussions on economic and social development. And I'm going to explain why that is and how we might go about changing that perception that engineering is really not relevant. And I think by the end of this talk, you will see how engineering is extremely relevant. And there are factors in engineering which explain why this stability and productivity difference has remained for so long. I want to illustrate the argument by considering the cost of a fundamental commodity which people can't do without, safe drinking water. Here it is being delivered, in this case in Jakarta, Indonesia. And the cost of that drinking water, when you work it out, is around about 70 to 130 US dollars for 1,000 liters, or 1 ton of water. It's not a very difficult calculation, just simply multiply the cost of 50 of those large plastic bottles. Here is the same delivery service operating in a different context, a refugee camp, in this case in Pakistan, and the cost here 35 to 50 US dollars for the same volume of water. So what you see here is the cost of unpaid labor by women and children up and down not only Pakistan, but many, many other countries around the world. And that the formula by which we calculate the value of that unpaid labor is exactly the same formula as, for example, in the US, you would calculate the cost-benefit ratio of building a new freeway or a new bridge to save commuters time when they try and get to work every morning. These are standard economic relationships that we use all over the world. And in Perth, the driest city of the driest state of the driest continent, the cost is 3 US dollars per 1,000 liters. Now, that's a startling comparison. And it's one of many that I've accumulated that show that wherever you go in the developing world, as soon as you ask for a commodity which is a comparable quality, comparable design, durability, all measures to what you would find the commodity in the industrialized world, the cost is less, surprisingly. It's more expensive for the poorest people on the planet. And this is an extraordinary situation and one that we could change. It also applies in other commodities, as I'll explain. So what we see here is that engineering is more expensive in the emerging world for the same quality, durability, and service quality. And the reason, without going into too much detail right now, I'm quite happy to talk about some of the reasons in the question time and discussion, is that for engineers, it's harder to secure collaboration and knowledge sharing. And what I'm going to argue is that the hidden curriculum let's face it, engineering curricula are the same around the world. And this issue, by the way, is not restricted to engineering curricula. The hidden curriculum of education rewards individual efforts. It doesn't reward collaboration. Now, if we could overcome these factors, we could see an immense increase in global prosperity. We'd see a huge improvement in resilience, adaptability, sustainability, and really importantly, engineers' earnings would be 5 times higher or more. You can ask me the logical links for this later. I want to emphasize this is not just an issue which affects the developing world. There are issues in engineering collaboration which affect the industrialized world too. So let's take this example. This is the Ravensthorpe nickel refinery. It was built at a cost of about 2.6 billion US dollars in 2008. In 2009, it was sold for around about 1/10 and closed. And in doing so, engineers who built the plant managed to destroy nearly $3 billion in value for investors. This is not an unusual project. If we look at the success rate for large engineering projects, over $1 billion, and here we're excluding building construction. And we define success, as shown at the bottom of the slide, as when investors receive at least 50% of the promised financial return. And if anyone thinks that's really a success criterion, think again. But if you have a tougher criterion, for example, 80%, then the performance figures will be far worse. The performance figures for projects over $1 billion, roughly 1 in 3 projects, 1 in 3 projects succeed. Yeah, just 1 in 3. Below $1 billion, we do a bit better, about 2 in 3 projects. And let me emphasize that out of 5 or 6 projects, at least one will be a complete write-off. And that is in the advanced industrialized world. If we look at projects which are operating, then some interesting work that came out of Scandinavia amongst leading oil and gas and chemical plant operators. These are the world's leading companies. Maintenance and operations mistakes were costing around 50% of turnover. 50%. And when you look at the way engineers do their work, you find that operations maintenance is regarded as a relatively low-level engineering occupation. As they say, good engineers get into maintenance and get out as quickly as possible. So what we see here is that there's a consistent pattern of significant losses being sustained by investors in engineering projects. And that's a challenge for all of us. You know, when I talk to engineers about this, many of them say, this is not an engineering issue. This is a management issue. This is a finance issue. But what I'm telling you today, as a result of my research, is that the people who make these decisions are engineers. They're very often senior engineers. And as a result, you find that engineers are not well regarded in boardrooms or even in governments around the world. In addition to that, we have, as all of you will be able to see by now, we have climate change. We've had for a long time environmental degradation, and we have pollution. We have widespread, stubbornly resistant poverty, which I've already referred to, the gap between emerging and industrialized countries. We have a widespread disdain for engineers in boardrooms and in companies and around investors around the world. Engineers complain about their low status. And so consequently, these are all challenges. But if you think about it, they're also huge opportunities for improvement. I understand that many of these figures may be surprises for many of you, but please listen on. So what's the basis of this? Well, this slide probably needs updating. It's actually about 19 years of research by 25 contributors in our research group. Most of those are undergraduate and graduate students, and I'm indebted to all of them for the immense amount of work and dedication they've shown through this research. We've based our work on a comparison of engineering practice between Australia, Pakistan, and India. Over 330 interviews with engineers, 10 field studies when graduate students follow engineers around for several days and note down every single thing that they do, and several longitudinal and occupational surveys. In other words, a rich data set on engineering work practices in, well, it's actually more than 3 countries, because we also did some work in Brunei and some other work in China and Malaysia as well. So what does the research tell us? Well, first of all, what we teach is only a small part of practice. Now that's true in any discipline, but just to give you some comparison, in medical schools, practically all of the teaching past the halfway point is performed by people who are practicing medicine every day. Now, how many engineering schools would that be the case? What we see is a consistent pattern where engineering is mostly taught by people who have very limited, if any, knowledge of commercial engineering practice. Engineering practice as a discipline in its own right is not taught. In fact, I think it's fair to say that engineering practice is an emerging discipline of research, and the knowledge of this research amongst engineering faculties today is extremely limited. Interestingly, engineers deny that most of their work is engineering. When we were interviewing engineers, one of the first things they would say to us is, "Why are you talking to me? Because I hardly ever do engineering." And then I would say, "Well, okay, what do you do when you do engineering?" And they would say, design, calculations, that sort of stuff. And of course, you have to wait until everybody's gone home, the telephone stopped ringing, and then you get a bit of peace and quiet, and you can do it then. So I'd say, well, what about the rest? And they say, oh, that's just admin stuff, meetings, contracts, negotiations, all that sort of stuff, you know. So, so why don't you hire an admin assistant to do that for you? Oh, well, I mean, you have to have the engineering knowledge to do it. Right. So it is engineering work. Yes, but it's not real engineering work. You know what I mean. Interestingly, students' critical thinking seems to get worse through their engineering courses. That's a really interesting piece of research which came out a couple of years back and should get us all talking very carefully about what's going on here. For a long time, we've known that university graduates have deficiencies in their ability in terms of creativity. Interestingly, students don't learn why we do engineering. If you ask students why we do engineering, they'll say something like solve technical problems, maybe make the world a better place. But beyond that, there's no clear understanding of what engineers' roles are. And this is a really troublesome one. What we found is a consistent pattern in which engineers neglect critical inspection and checking work in their practice. Engineers can't explain the value of their work to others. So consequently, when companies downsize, very often the first target is engineers, simply because they can't explain why companies should employ them. So as I said, these are challenges. Well, they're all opportunities for improvements. So where do we move on? Now I want to talk about some basic ideas around productivity improvement and value creation. And much of this comes from economics, but they're very simple economic principles, and I'm quite happy to discuss them in more detail later if needed. So I argue that engineering is performed by people with specialized technical knowledge and foresight. These people conceive, deliver, operate, and sustain man-made objects, processes, and systems that enable people to do more with less effort, less time, less materials, less energy, less uncertainty, less health risks, and less environmental disturbances. Now notice I do not say less cost, because actually cost depends on choices that have to do with all of those factors. But these are the attributes that become apparent from our research on engineering practice. Interestingly, what it's basically saying is that engineers are responsible for improving productivity. And if you go back to the 1950s, the Grinter report produced by the ASEE, which looked at how engineering education should be reformed, and that was extremely influential at the time. There was a clear understanding there that engineers were supposed to be the people who improve productivity, industrial productivity. But that emphasis on productivity improvement has disappeared from our definitions of engineering over subsequent decades. And really interestingly, if you look at what's happening around us, you will find that productivity improvement, which was steady through the 1960s, 70s, 80s, and 1990s, has now slowed to a crawl. And it was that reduction in productivity which seems to have triggered the global financial crisis of 2007, 2008. Now, I'd like to put this to you. If we don't teach young engineers that their job is to improve productivity, how should we expect them to do it? Right? We don't tell engineers that this is their fundamental role. So it's no surprise that when they come into practice, that they don't actually do this. And consequently, we're not seeing the kinds of improvements in productivity that we used to. Why are these productivity improvements important? Well, this is the crucial point of this talk. As I said, the key difference between developing emerging economies and advanced industrialized economies is productivity. And so consequently, what I'm arguing is that it's the role of engineers in emerging economies to improve productivity. But it's a tall order. It's difficult. Extremely difficult. And I'm going to explain why. So let's now talk a little bit about educating engineers, and some of these issues will start to become more apparent to you. So what do we teach? Well, we teach engineering science, and I must say we do a good job of it. It's very rare that you will hear of an engineering failure which was caused by a mistake in calculations or understanding of physical concepts. What do we not teach? Well, we don't teach technical planning and foresight. We don't teach technical collaboration, which I argue is specialized ways of collaborating that engineers have evolved over centuries that enable practical results to be delivered to clients that more or less meet their needs and expectations. Engineering science is typically 2 to 20% of practice. One of the really interesting findings that came out of our studies was that electrical engineers spend the least amount of time on engineering science activities, around 2% of their practice, their work time. At the other end of the spectrum, environmental engineers were spending up around 20% on average because they do a lot of modeling work. And the technical planning and foresight, by subtraction, is 80 to 98% of practice. That's what we don't teach. Now, that wouldn't necessarily be a problem if what we taught enabled students to pick up technical planning collaboration activities easily, but that's unfortunately not the case. The other thing we don't teach is why we do engineering. I'll come back to that. So here is, if you like, a quintessential picture of an engineer at work. I had to ask my engineer at the time to pose for this photograph because he did it so little. We think of engineers as problem solvers, but when you actually ask engineers about what they do in their careers, they solve so few technical problems that they can remember every single one of them. It's not like they're solving one a day or two or three or four a day, so that it becomes simply a vast number that they can't accurately recall. Engineers do lots of things, but they don't do technical problem solving very much at all. So what do they do? Well, if you believe our engineering education, what we're doing essentially is we're training students at universities to write mathematical solutions for narrowly defined technical analytical problems in exams. That's basically what we're asking them to do, and that's certainly what we reward them to do. That's how you get your grades in universities. And when you hit the workplace, this is my picture of what happens. Look, it's tough. It's tough for students to learn how to do that, and we've got a couple of students on the left-hand side of the picture running up that slope. They jump out into the world of employment and they land very heavily on their backsides and wonder what on earth has happened to them. Because those first few weeks in engineering employment, for most of them, are like nothing they expected. Then they pick themselves up, they sprint very hard, they try and work hard, and then they suddenly find themselves literally hitting their heads against a brick wall. They don't understand why they're not getting anywhere with their careers. And the sad thing is that many leave. You know, a vast number of engineering graduates in South Asia go into writing computer software. And isn't it curious that they should be more highly valued for writing computer software, which is something that they've not been taught to do in their studies, than for doing the thing which they should be learning how to do in their studies? Something is going very wrong. So here's a view of engineering practice. It's one of the views of engineering practice that I've used to describe the results of our research. We have across the top part essentially a series of intellectual exercises. We have identifying client and society needs, conceiving future solutions, and predicting the future. I want to see if I can get a better pointer on this. Here we go. Predicting the future. And then we have all that leads up to an investment decision. Somebody has to put up the money to convert a pile of documents into something real. And then if they say yes, then the engineer's job is to deliver the predicted future on time with predicted cost, performance, safety, and environmental impact. In other words, to make it work pretty much as well as the clients were led to believe. We don't exactly do that. We get somewhat close to it, but in doing so, we learn a lot, which means that we can become better at identifying client and society needs and conceiving future solutions. So that's basically what engineering practice looks like, you know, in the way I've sketched it. And let's look at what we teach. Okay, the green ticks here and here. We don't teach all these other things. And then it is no surprise that all these other things are the bits that engineers regard as not real engineering, because it's simply not part of their studies. And if it's not real engineering, then they're not motivated to learn how to do it better. They just see it as an imposition, something that gets in the way of the real engineering, which is doing design and calculations. They describe it as non-technical work, but when you listen to their conversations as they're actually performing this work, it's thoroughly technical. This is just simply a perception. Now, here's another way that I use to represent engineering practice. The 3 cups of tea, they're there because my wife loves tea. My wife was born in Pakistan and she's thoroughly addicted to tea. So I say, well, this is the what you get out of doing engineering. Essentially 3 kinds of value. One is client satisfaction, and that's really important because when the client is satisfied, they'll pay your bills. The second is achievement satisfaction. In the words of one engineer, he described it to me like this. He said, I take my daughter out and I say, see that funny little yellow thing that's sticking out on the side of that tall thing that's sticking up from the blue bit? That yellow bit is the bit that I designed. And the daughter says, oh, did you, Dad? That's the achievement satisfaction. And then finally, reputation, because reputation is what brings more work. Really important. And all those 3 rest on a whole series of complex technical collaboration performances and this business of technical and financial foresight planning, the ability to think, what do I have to do to get this job done? And those rest on 3 pillars. Certainly, engineering and business science is critically important. And the colored bits, by the way, indicate how much we teach in universities. We teach a fair bit of this. And of course, these days in many universities, engineers do business courses at the same time, or they do it afterwards as an MBA. But there's 2 other legs which hardly get mentioned. One is I call tacit ingenuity. Tacit knowledge is knowledge that we have in our heads, but we're not aware of it, like how to ride a bicycle. That tacit knowledge is what enables us to be creative. And yes, it's an important part of university studies and it comes from practice and so on, but we don't talk about it very much. And yet it's critically important in engineering practice for the simple reason that most engineering decisions have to be taken very quickly. And the only way you can take quick decisions is on the basis of tacit knowledge which you've accumulated in your head. You don't have time to go through the full reasoning. That's something that's done later when you come to write a technical report. And then on the left here, we have listening, reading, and visual perception. When we talk about communication skills in universities, most of the discussion is about writing. But actually, it's listening, reading, and visual perception that are really important skills, because that enables engineers to understand what they need to do. Without that, written communication is of very little value. So this is an interesting question. Since we know that engineering now relies on collaboration, can we teach collaboration in universities? Well, I argue that there are several obstacles to this. First of all, assessments are almost entirely based on individual performances. And so every time students undertake an assessment, we are reinforcing an association between rewards, that is grades, with individual work. And this shows up as a resistance to assessments based on group performance. When you try and get students to do a group project and you tell them that they're all going to get the same mark, many of them get extremely uncomfortable. And this is because we are undermining this deeply seated idea that emerges all through education, that your assessment should be based on your individual performance. What I do is important, not what they do. And also in many universities, we label collaboration as cheating. Now, there's another factor in here that written assessments here create an implicit valuing of written communication. Once again, we associate grades with some things that students write, or at least make a mark on a computer screen in a multiple choice test. And as a result, what we see is a loss of oral skills. Oral skills are sidelined and don't develop through university education unless students get really involved in extracurricular activities, which is becoming less and less common these days because students are seeking part-time work opportunities for economic reasons. So what we see is that their oral skills are not developed, but these oral skills are essential for building trust, for collaboration and leadership. And then, surprise, surprise, employers complain about communication skills. Well, really, what employers are complaining about is their inability to collaborate, but it's labeled as communication skills. And as I said, maybe extracurricular activities are a way to start addressing this. But I've argued elsewhere in a forthcoming paper that we really need to think more seriously about this issue. Now, in case you're wondering, a lot of this has been written and it's available in my book, The Making of an Expert Engineer. And as a special offer for this webinar, if you email me within the next 2 weeks, I will arrange, particularly if you're in a country like India or Africa, I will arrange for a paperback copy to be sent to you. So just get in touch with me by email if you want to take me up on that offer. You can't get access to it. It's quite expensive.
Wow.
And there's also this guide.
That's good. Go ahead, keep going.
Yeah, this guide for value creation, which is available on the website. I'll give you at the end of the talk in a couple of minutes. Now, one of the other interesting things that came out of our research was that graduates emerged with over 100 mistaken expectations about engineering practice. And these expectations make it more difficult for them to learn about what practice involves. I'm quite happy to give you papers on this too, if you want. Some of the examples of these misconceptions, that socio-technical factors, communication, collaboration, and so on, that they're non-technical issues, whereas in fact the evidence shows that they are thoroughly technical in the engineering context. Many graduates think or students think that engineering is a hands-on occupation, and many of them choose engineering because of this misunderstanding, and then get very frustrated when they get into practice and find out that they don't have their hands on anything. This is a really interesting one. Engineers believe that they're naturally logical and more logical than other people in other professions. And this idea is extremely persistent through many decades of engineers' careers and is not based on any evidence. Engineers definitely prefer, and they think that they're working with objective facts stated in numbers, when of course they overlook the fact that the numbers are defined by words, and the words can be anything but objectives. As I said, engineers believe that they're problem solvers and they don't do much problem solving, except of course in the sense that we all solve problems. For example, when if you have to get on a bus to get to work, you've got to figure out what's the best place to get on the bus, what's the best place to get off. If the bus gets stuck in a traffic jam, should I walk? Should I try and get a taxi or whatever? We all solve problems every day of our lives. Many, particularly female engineers, think they need to know it all and are very self-conscious of the fact that they don't know it, when in fact, of course, they don't need to know it. And another good one is that self-learning is needed because technology keeps changing. Self-learning is needed because engineers need to learn practically everything they need on the job. It's nothing to do with technological changes. And there's another 96 of them. If you're interested, read the book. So I argue that there are unprecedented opportunities for engineers who get it right. I don't know how many of you have seen this. This is the latest, as far as I know, the latest climate change forecast from the IPCC, the International Scientific Community, which shows that we're going to get to this target of this ceiling, desirable ceiling of 1.5 degrees of global warming around 2040, unless we do something pretty promptly. And the scientists are now arguing for reduction in CO2 and other greenhouse emissions from our present levels to reach zero desirably by 2040, at the latest by 2055. Now, we're only going to achieve this with massive changes. And what's happening around the world is that companies have realized what has to happen. Governments are dragging their feet in many cases, but companies have certainly realized what they have to do. And there is building up from now an unprecedented demand for engineers who can deliver on this. Everyone will need new machines and processes to eliminate their greenhouse emissions. We're talking there, of course, about net greenhouse emissions, not greenhouse emissions can be offset in different ways. And I would say this is the biggest opportunity for engineering in centuries, because engineers have more influence over greenhouse emissions than any other occupational group. Get in there, do it, earn some money. And these are some of the companies, just 3 examples that I collected for a talk about a year ago. Coca-Cola is transforming all of its plants around the world to work on renewable energy. Batteries are being installed all over the place and are even profitable in order to provide the backup storage for renewables. And Blix is a mining company, interestingly, that spotted an opportunity. Customers will pay more for metals that are made using green processing, that is in a sustainable fashion with 0 greenhouse emissions and 0 pollution. And they're actually building mines right now with this objective in mind. Now, I said I was going to talk about UN Sustainable Development Goals. Essentially, my argument here is quite simple. All of these goals require productivity improvements. That's the bottom line. We're not going to achieve those goals without very large productivity improvements across the globe. And so essentially, this business of closing the gap between developed countries and developing economies, that's all about productivity improvements. So the UN Sustainable Development Goals. For example, if you want better gender rights across the world, we need people who are expert in that area. They need to be educated. We need people who can be spared from the workforce. And definitely in a country like India or Pakistan, if you look around you, the number of people who are available to do these things is tiny. The reason? Because virtually the entire working population is required just to meet basic necessities: food production, water, shelter, and clothing. You know, in India or Pakistan, you'll find somewhere around 40 to 50% of the workforce is involved in agriculture, subsistence agriculture, whereas in an industrialized country, it's around 2 or 3%. That's the kind of change that we have to make in order to improve productivity. So the observations, my observations, and Krishna, I promise I'm going to finish in a second or two. Sustainable development relies on productivity improvement. Engineering has been almost completely overlooked. If you go through the UN documents, it's hardly mentioned. And for less developed countries, what we have is a situation where social culture and language shapes collaboration and trust. Collaboration and trust in turn shape engineering performances and form societal barriers. That is, there are certain kinds of engineered systems like water supply and electricity supply which just don't work well in developing societies. On the other hand, mobile phones work really well. So as engineers, we can't solve these societal problems. We need to learn how to work around them. So I'm arguing that engineering education could be significantly improved. And getting collaboration could be very difficult, but certainly talking about productivity improvement, I think, is very straightforward and easy for all of us. We need lots of examples of sustainable products that cross these barriers, and we need to think about reshaping this hidden curriculum. And I argue that Close Comfort, this is the product which I've spent a lot of time developing over the last few years. This product is one way to break through these social barriers. It's a very simple device, plug it in and get your cool air, and dramatically less spending on energy than you would with conventional air conditioning. So here's my suggestions for you. Collect data on real costs in your own environment, including this shadow-priced value of unpaid time. Critically to understand that, and you'll find it in my book. Ensure that engineers understand indirect costs, the costs of supervision, cost of control, and that's chapter 11 in my book. And identify products and services and the extent to which social barriers are influencing end user costs. That's quite an agenda for you. It'll keep you busy for a while. And here's some reading. that is, Krishna, to note, people who get a copy of the presentation, you can consult that list later. And I just want to say that in my spare time, I take beautiful pictures of the beautiful flowers we have in Western Australia. Wow. And there's some websites for you to use as references. And over to you for some questions and discussion.
James, that was such a fascinating and educational and inspirational presentation. Thank you so much, James. Amazing. We have time for some questions, and I want to make sure that whoever wants to ask questions gets a chance to do that. We may not have time to answer all of them, but I want to let you know that the recording of this webinar will be available, and all of you who attended will automatically get one. But if anybody else would like the recording, we'll send it to them also. Yeah, questions coming in, and let's see. Elizabeth Harrison says this is interesting about students and critical thinking. Okay, so what is the view of when to teach engineering ethics?
Good question. So in my research, one of the things really interesting things that came out is that ethics has an instrumental value in engineering practice. So engineers, by and large, secure collaboration through trust and respect. And that trust and respect is seriously undermined if it becomes apparent that engineers are not ethical. So I talked about this a little bit more in my book, and I'm happy to correspond and send references if you like. But that's I think is the underlying principle that we need to understand, that engineers need to be ethical in order to gain the collaboration and respect of others. Now, there's also moral principles involved, but I think that once, if you argue on the basis of morals, many students simply say, oh God, I don't really want to know that. But if they understand that it has a real instrumental value and it's going to help them practice more effectively as an engineer and get more respect, then I think that might shift the equation significantly. And I've not seen much emphasis on that in the discussions on teaching engineering ethics.
Elsie, would you like to ask a question yourself? Elsie Mayo?
Yes, I would. Thank you very much. James, it's always wonderful to hear you. And I'm so happy for this opportunity for you to present in the long form. So I've just come from the previous webinar that Krishna hosted, which was about outcome-based education. And I can't help but sense and comment on the parallels with that conversation, this one, and the challenge that we have in business management and the opportunity. From my lens, what I'm seeing is the threshold that we're all on is one of noticing the context in which we are doing whatever we're doing. So if you're in the process that you first mentioned, identifying what's the client need, putting that in the context, what are the emergent trends, if you will, the external environment. And in a way, this requires an integration of what our objectives and views are from the business point of view or the employer's point of view. And importantly, what's missing in the conversation, as you've pointed out in the UN papers, et cetera, is the ingenuity and kind of innate wisdom and lens of the engineer to help us understand what is actually possible in the physical world.
Yes.
So,
yeah.
So my question or my invitation is for us as different disciplines to see that this is the point of power. It's where our different lenses come in to identify the problem and the opportunity that only we with our unique capabilities can do together.
Look, I think you make a really good point there, and it complements what I've been saying. So thank you very much. Perhaps I would talk about a student whom I met a year or so ago at a presentation in the northwest area of Pakistan, and he said, "Look, I've listened to everything you've said, and I'm really worried because as an engineering student near my final graduation, I know nothing about any of this other stuff. So why can't my company hire a manager to shadow me and help me with all these things? And surely then I would be much more productive as an engineer. You know, I have a clerical assistant, I have a manager, and so on and so forth. I can just focus on the equations, and they can do everything else. And my answer was, well, I'm sorry, but actually you can't do anything in engineering without money. So for a start, you have to understand the finance. And if you don't understand the finance, you'll be left out in the cold, and you'll be almost powerless in the organization. So the catch here is that when we talk about business and finance in engineering schools, the response is usually, oh, well, that's something that's taught in the business school. And when you talk about technology in the business school, they say, oh, that's taught in the engineering school. And so there's really very little common ground, and any educationalist will of course, will tell you, which is something that we actually observed, that graduates who, even if graduates have studied in both schools, that is, they've maybe done an MBA and an engineering degree, when they get into practice, they can't make the links between the two. It's quite unusual for them to be able to do that. And so one of the interesting things that came out of research I did with Bill Williams recently was to suddenly discover that there was actually no literature that explains how the vast majority of engineering produces economic value. So it's not just a question of, if you like, thinking in isolated silos, which has been a tendency for a long time, but it's also the lack of serious intellectual inquiry which links these disciplines. And I would argue that very often that explains why it is hard for students to draw the links. Even if they want to understand the links between the two, there's very little that they can grab a hold of and help them understand.
Bill, do you want to jump in? Bill Williams?
Yeah, thank you, Krishna. Yeah, seeing as James, you've given me a name check, not so much a question, more a comment. You mentioned about the data that you and your colleagues had gathered from Australia, India, and Pakistan, and also China and Brunei. It's worth mentioning that the data that we gathered in Europe, in Portugal, showed exactly the same picture, really, about engineering practice being that collaboration is a central part of engineering practice, and the question of value creation isn't in the mind of the engineers that we spoke to here in Portugal, just like, as you said, in the other parts of the world.
Okay, great. Milind Siddhupura, you wanted to say, talk about project-based learning. You want to jump in?
Yes, hello James, a very interesting presentation. I'm Milind from EIT in Perth, Western Australia, from your home.
Yes.
And quick question about, as you were mentioning that, that engineering education doesn't teach the core skills which is required, entrepreneurship or the communication or they just focus on the mathematics. So do you think if we focus more on project-based learning with sustainability focus built into it, and students actually try to improve the products or processes during their engineering education, would it solve the problem? Because we are aiming for zero emissions in a few years' time.
It can do. Project-based learning can be very effective, but it needs a lot of involvement, and students need a lot of continuous feedback. Now, there's some really interesting stuff that's just come out, and thanks to Jenny Case, because she highlighted one particular paper to me, which has provided us with a meta-study of an enormous number of different educational approaches in the context of higher education to find out which ones work and which ones don't. Or at least, of course, there's a spectrum of effectiveness in between. And what that's showing is that project and problem-based learning, depending on how it's structured and delivered, can be extremely ineffective from an educational point of view, particularly if students are left to sort things out for themselves. But if given the appropriate direction and feedback, can be extremely effective in helping them to integrate ideas across different areas of discipline. So a lot depends on how it's delivered. We should not automatically assume that this is the solution, There are many others, and I'm quite happy to, if anybody wants to write to me, I'll provide that reference for you.
Okay, great. So a lot of colleges are doing engineers without borders and engineering projects and community service and so on. And I think the same problem that you mentioned, James, that you have to have faculty who know how to guide the students rather than just leave the students alone by themselves. So what do you think about these kinds of activities in various colleges?
Well, look, they can be very effective at motivating students, but at the same time, and I think this applies particularly in, if you like, the Western world, I think that Engineers Without Borders projects give students a totally distorted idea of what the developing world is like. And they think that the whole developing world consists of people living in thatched huts with bicycles and very little else. And that's very, very unfortunate. And I think that needs to change. But it can really only change by collaboration between universities. And that's where I think there's a real scope for universities to form collaboration networks. You know, the unfortunate trend is that most universities only want to collaborate with universities that they think are better than they are. And I think that we need to build networks which actually embrace a whole range of different universities, because the developing world actually has really intellectually challenging issues and problems. And the reality is, given the level of resourcing, the reality is that these problems actually can benefit enormously from intellectual horsepower that's available in advanced countries, but only if people in advanced countries really understand what the ground truth reality is like. So I think, and that's you know, that's something which I've come to appreciate. That's happened as a result of my life experiences, and has led to some very interesting innovations which I'm now pursuing. So it's a profitable area to get involved in, and a very intellectually stimulating one. So I thoroughly recommend it, and I just wish lots of other people would try it.
One of your friends, Arnold Pearce, is with us. He just says he's nice to talk. Nice talk, James. Hope to have time to meet up and chat. I'm in Australia from 11th of December in Melbourne. So Arnold, you want to add any comments? You can unmute yourself if you want to do that. I've unmuted you. Arnold? Otherwise, we'll just leave it at that. Okay, so yeah, we are getting a few other comments, but I think, you know, let's see. Get up here. Some of them are rather lengthy, so I'm trying to sort it out. Okay, one question is, do you plan to make any, do you really appreciate your presentation? Do you propose to make any document regarding sustainable development goals and the roles for engineers? Is it all, maybe it's already in your book, right? I think that may be.
Yeah, it is. There's a chapter in my book which is particularly relevant for developing countries, chapter 13. And perhaps I would say that at the top website there, I actually have published the initial chapters of a new book, which I'm now writing, which essentially is to make the material in the first book much more accessible to students and young engineers. So if you follow that and read the chapters as they come out, you're welcome to provide me with comments and feedback before it gets published.
Bridget Ogwezi, let me see if you want to talk yourself. Bridget, let me see. We'll just take one or two more questions because we're out of time. Bridget, you want to ask your question yourself? Bridget, come in. I've unmuted you.
I don't.
Bridget, yeah, come in.
Oh no, I was just.
I'm not able to hear you clearly, so I'm going to read out his question. Excellent discussion just now, but how certain celebrated engineering education activities don't always have the intended outcomes. We need to broaden the thinking and collaboration with developed and developing nations. So that's her comment. And LC once again says what? Yeah, go ahead. Go ahead. I think, yeah, we need to wind up maybe in a minute or so. Any final comments from you, James?
Well, look, as I said, I'm quite happy to engage in discussions by email. Maybe we can have another sort of offline chat session or by some other means, Zoom and so on and so forth, I'm quite happy to do that informally. And I wish you all the very best. And I've set you quite a challenging agenda there in terms of reading and some data gathering. And I invite you to participate and carry on the good work. Thank you very much. Krishna, for inviting. Thank you so much for the audience for taking the time to listen today.
Have you been to India recently, James?
My last visit was a couple of years back, and I'm planning a new visit in the coming months.
Oh, okay. Well, maybe we can keep in touch and see if we can connect you with the engineering education trial work that we are doing in India through IFES and IUC. Okay, thanks a lot, James, and good luck to everybody who has joined us for a fascinating discussion. And I can see this is just the beginning. I'm not sure how best to keep this kind of conversation going because so many exciting questions that are propping in my head and everybody's head, and it needs to have a forum where we can continue the discussion, but we'll figure that out. Okay, thanks, James. Have a good day.
Thank you, Krishna.